Welcome to a new episode in the Multiverse video series. Today we're going to learn how to do gradient descent using R. Gradient descent was a tool introduced in the deep learning video, which is a great procedure to train networks of perceptrons or even deep neural networks. However, I don't encourage, and you shouldn't be training networks using this technique by hand. There actually happens to be the case that better tools exist to help you do this much faster and much more reliably. Other videos will introduce the TensorFlow package and the keras package, which allow you to do all these gradient descent and much more detailed functionality using a higher level API without having to differentiate by hand. So again, this is a video mostly to learn about gradient descent, but it's not something that you would want to use in your data analysis. So the previous video introduced the concept of a perceptron. A perceptron happens to be somewhat similar to a linear classifier, and we mentioned that we can chain these perceptrons together to create a network of interconnected perceptrons, which is usually defined as a neural network. So for us to follow along, let's start working on an R notebook. And let's just say, let's just first define the perceptron, just mathematically, right? So the perceptron mostly looks like this. We can call this P of X, right? And there's two cases. One case where the perceptron is activated, and one case where the perceptron is not active. So when the perceptron is active, we want to activate the perceptron when this linear classifier goes over a threshold, B, right? And in any other case, we want to say, we'll basically, in any other case, we'll output 0. So this is the definition of the perceptron, and it happens to be quite useful to just write it by hand. All right. So what is the next step? So usually you would have a network of perceptrons. This is what is called a neural network, and the network usually looks like this. There's one perceptron with input, and that perceptron produces output, which can optionally be connected to hidden layers, and those hidden layers of perceptrons can also connect to an output layer. In deep neural networks, you usually just have significant number of hidden layers, and it's rather much more complex, but the way in which you would use gradient descent is quite similar in any case. So quick refresher, what is gradient descent? Well, gradient descent is mostly a technique introduced by Jeff Hinton to optimize a function into its minimum. So the way that you would optimize a function with gradient descent would be simply by calculating its gradient, and this would mean differentiating the function. And then what you want to do is over each iteration, you would want to follow that gradient in order to minimize the function. That's pretty much the definition of gradient descent. So let's just move this to our R notebook, and basically all we want to say is this algorithm in nature is iterative, right? So we're gonna say that we want to start on some given step, which is an, and then what we want to do is we want to do two things. We want to follow the gradient, but we also there's a parameter known as the learning rate, and the learning rate is just a constant. It basically controls how fast we move on the given given gradient, right, which is represented here, and the gradient operates over the previous step, right? We evaluate basically the gradient on the previous step, which is a of n. So that's pretty much it. We start in a random step in a random set of initialized weights, and then we basically move on the direction of the gradient with a given learning rate. So let's just define let's define f just yeah, for simplicity, since we're gonna be using this, not really, not really the perceptron, but the linear classifier part of the perceptron. Let's just define it as, yeah, it's a function, right? It takes some input, which is x. It has some weights, and it has a bias, right? And basically, what we're doing is just multiplying the weights by the input, and then we have a bias. And this function is going to be useful when we start writing the code for this. So that's great. We know the gradient, and we know the the structure of our perceptron. However, one of the challenging things here is that if we were to look at the step function, so let's just look at step of x. This would be the standard perceptron as was defined by Rosenblatt. And if you look at this function, right, I mean, so the gradient, the derivative here is 0, then it doesn't exist on 0, and then it's also 0 again. So this function is not very nice in terms of being differentiable, right? It's not very helpful to actually train using gradient descent, because it's pretty it's not continuous, and it's pretty constant, right? So it doesn't help us that much. However, there is a function called the rectified linear unit, which is pretty much a step function, but it happens to be linear between 0 and 1. So how does that look like? Let's see. So that would be the ReLU function, and it looks very similar to the step function, but it happens to be, a little bit more friendly in terms of differentiating the function when we compute the gradient. So this is how the ReLU function looks like. It's still 0 below 0. It's not differentiable in 0, right? Like it just doesn't exist, the derivative at that point. But if you look at the rest of the function, the derivative of this function is just 1. And it just happens to be a function that is more useful when doing gradient descent than a step function. There's other functions that we could consider, like the sigmoid and why not, but ReLU is definitely one of those functions that is quite easy to use and recommend it. So in this case, we're gonna let's define the ReLU function. And so as I was mentioning, this function that we're going to define our perceptron as p of x, and we're going to say that is the max between 0, right? That's when the function goes below 0. We want it to be 0. And then there's just our linear classifier that we have here, and that's pretty much it. So this would be a nicer perceptron than what we have here. As I'm mentioning, this one is not very nicely differentiable and doesn't have a lot of nice properties, but the ReLU does. So that's just one optimization over it. All right, so we're pretty much done with the setup. Now we need to minimize the function. So what function do we minimize? We don't want to minimize the perceptron itself, like that. That's just a function. It doesn't have a lot of value. What we want to minimize, we want to minimize. So the function that we really want to minimize is the error function. We want to, let's just name this function the loss function. And this function is going to have some parameters that are interesting to minimize. Actually, x is going to be constant. But the parameters that are interesting to minimize is the actual weights of the perceptron and the bias. Those are the values that we do not know. However, we do know the inputs of our neural network. Those are the things that the neural networks is getting into, and we have the outputs. So let's see. So what we really want to optimize is the value of the perceptron at any given point x for some given weights and some given bias. And we want to compute the error against the output, right? So we say if we're trying to classify like a letter A or a letter B or something even simpler, we want to figure out what's the difference between the output of the network, in this case a single perceptron, and the given output. And we can use the square loss or whichever loss metric you want to use. And that's it. So this is what we want to minimize. We want to minimize the loss function. We don't want to minimize the function itself. So what exactly is this? Well, if we just replace the terms, what we want to minimize is basically our adjusted ReLU function, right? That is operating over this simple linear classifier. We remove y, which is our output, and we just keep the loss squared. Okay, that's pretty much it. So this is the function that we want to minimize. Now, for this particular example, I'm using a pretty simple neural network, which is a neural network with only one perceptron. No hidden layers. It's very, very simple. If you wanted to do this on a bigger scale, you would have to consider chaining this perceptron to the output of another perceptron, right? So this would look something like, like P of X would be the output to another perceptron. The input would be the X. So you would have a different set of weights. You would have an input from another perceptron, and you would have like a different bias, right? So it would be bias 2, weights 2, and why not? So this would be a network with one perceptron chained to another perceptron, etc. So obviously the math gets more and more complex, the more perceptrons you have, and that's one of the reasons why we use other tools like back propagation and also packages like TensorFlow, which we can do all this for you automatically. Okay, so let's differentiate this function, right? So what we want to do now is compute the gradient, right? So what we want to compute is we want to compute the gradient of this loss function over these parameters, and again x and y. Oh, actually, yeah, it would be b. These parameters are actually some of the parameters are fixed, right? Like x and y, because we know them, right? This is functionality. Sorry, not functionality. This is data that we have from the model of what we want to classify. The parameters that we don't know are w and b. Those are the weights that are actually training our neural network that we need to figure out how to find, right? So we have these. We actually want to differentiate over multiple. A few things, right? We want to if we have only one perceptron, and I'm gonna keep things simple here. W could be a vector, and B could be a vector, so it would look similar to this, right? Like we would have to calculate these two. We would have to differentiate this function over W and over B. However, to keep things even simpler for this particular example, what we're going to assume is that there's only two weights. So we're only going to have a very simple classifier that takes two weights, W1 and W2, and there's a bias. So our perceptron is going to be very, very, very simple. But it's still the same math and the same process would work for complex networks. Right, so we have that, and now we need to differentiate. So we need to differentiate this function, right? And in order to differentiate this function, well, first we are going to differentiate the first term, which is 2 times, and then our ReLU activation. And then we need to differentiate the ReLU activation, right, by the chain rule. And so we already know the answer to this. If you look at ReLU, if you differentiate the ReLU function, the function that describes its derivative is the step function, right? We need a function that is 0, below 0. It shouldn't have a derivative on 0 because it just doesn't exist, and then it needs to be 1 on any other value that is higher than 0, right? And that happens to be our step function. All right, so let's call our step function theta, and we're gonna do f of we want to do w, x, and b, right? So now we have differentiated basically the inside, the linear part of the. Sorry, we have just differentiated our ReLU function. We have our step function now, and now we need to differentiate the thing inside it, right? Which in this case, if we are differentiating wx plus b, and we're differentiating over w1, what we would end up getting is just x1, right? because b would go to 0 and w that we're differentiating, and it's just 1. And this is actually quite similar for w2. I mean, it's basically just the same, but we would just get the value w2. And then for the bias, it's similar, but when we differentiate w times x, that would be 0. And when we differentiate b, that would be 1. So we basically end up just having 1, right? Or nothing whatsoever. All right, so we're pretty much done at this point, at least with the math, right? We finished the math, we're done. And now let's actually compute gradient descent. All right, so in order to compute gradient descent, what do we need to do? What do we need to do? So let's just actually first take a quick refresher on what gradient descent is. Again, a previous video introduced gradient descent, and if you remember, we might have mentioned that there's a different ways of performing gradient descent. The most basic one, we just call it gradient descent, and there's other variations like a stochastic gradient descent and back propagation. So for this particular video, we're going to focus on just the most easiest simple case of gradient descent, which is just gradient descent. And the way that it works is basically we need to repeat until we converge. Either in this case, I'm actually going to keep I'm going to keep this simpler, and I'm just going to repeat until some arbitrary number, right? So we're going to loop, and we're going to basically compute the value of the function f of x, which I think in this particular case is the whole network, right? Is the value of the network. And then what we're going to do is we're going to adjust using a learning rate and our gradient based on the next iteration. So how would that look like in code? Well, first of all, we need to initialize the weights. So in this particular case, we're going to initialize the weights, say let's 0.1 and 0.2. It just doesn't matter. It needs to be, well, it actually does matter as long as it's random and as long as it's a small number. And there's also a lot of other theory on how to initialize weights properly, but let's not care for this particular video. And we need a learning rate, right? So we're going to call it learning rate 0.1. All right, so now we need a problem that is interesting to solve using gradient descent. And kind of like some of the hello world, perceptron and neural network examples are usually, you will usually find that, a good way of testing these with truth tables, because they have so very little values, but they're still useful to conceptualize what you want to train. So in this case, let's just assume that the problem that we have is, we have a set of inputs that we're going to call P and Q. And they can, all the values, if we're talking about logic values, all the values that it can take is either truth or false, right? So, we can have true, 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 false, false, true, and false, false. That's it. It only has 4 values. It's very, very simple. And then we can choose one of the outputs, right? We can choose, for instance, an AND function. And the AND function basically says whenever the 2 values are true, you want the output to be true. In any other case, it's false. We could pick some other ones. Some of them require, as we mentioned in the previous video, are not possible to train with only a single perceptron, like the XOR, but you could definitely chain multiple perceptrons and train it in that way. So we're going to focus on and we need to define a truth table in R, and then basically our response variable would be the values of the AND column. Right, so let's just define first X. So X, again, X are our inputs. So let's define this as a matrix. And the values that we mentioned that you find on the truth table is, you basically have like all the different combinations from having true and false on that truth table. Let's see how this looks like. Actually, I might need to do X here. And I might not need this. Right, so this is how our truth table looks like, right? 0, 0. In this case, we want the value to be false. So we're going to say that in Y, we want this to be, let's just align it. In Y, we want this to be 0. Then we want it to be 0 again. Then we want it to be 0. And then we want it to be 1. And again, this is completely arbitrary. I mean, it's based on a truth table, but in practice, you could be classifying anything potentially with a neural network. In this case, we're just picking a truth table as an example. All right, so we have defined our truth table. So what is the next step? Well, we actually are ready at this point to start training our neural network. So what we're going to do here, let's just define this. All right, so we have this defined. Now, what we want to do is, we're still missing to define f, right? So f, as we were mentioning, is going to take w, x, and b. And this is going to be a function, right? And what the function will have to do is multiply, and we can use this overloaded operator in R. I think we'll have to do the transpose of x plus b. So let's see if this actually works. Function. Right, so we've defined f, and then this should return the value of the gradient at this particular point, since everything is initialized. All right, so we have the value of our basically of our function at this particular point in time. So that's not exactly what we want. What we want to do is we want to do something like this for I in 10, right? We're going to do 10 steps, and now we want to basically be able to iterate over this function and follow the path of the gradient, right? So we're going to say that W1 or W, right? W needs to be something. W needs to be the same value of W, right? Minus the learning rate, right? Times our gradient, which we have defined over there, but not yet. So let's see. So we have our gradient is gonna, and we have for W1 and W2. So what would this gradient be? It's gonna be 2 times, it's gonna be 2 times, and then the max between 0 and f of W, X, and B, right? So that's, minus Y. So that's the first piece, and then we need the step function. Maybe there's, I bet that there's a step function in R already. Anyways, but our step function is basically gonna be, yeah, and do if else x bigger than 0, then we're gonna do 1, otherwise we're gonna do 0. All right, so this is gonna be our step function. So we can say step, and let me scroll up, step, and then we're gonna do again the value of the function, right? And then times x1. This is my this is my first value to compute W1, and then to compute W2 we do exactly the same, but we do W2. Let's see if this works first. Argument 3 is empty. Okay, this we need to remove this comma. So right, this is the value of the gradient. Well, actually, it's not just the gradient, but it's the gradient plus the learning rate for the first iteration. So this is looking promising, but we also need to adjust B, right? And the value of B is gonna be pretty much the same, except that we don't have this last term, right? And then what we want to do is we want to the other thing that we need to do is we're working with vectors, but we basically need to either do this over each vector, right? Like we need to do it once for x1, x2, x3, and x4, because as you were looking here, we actually have the results of not just evaluating one gradient, but evaluating all the test data over the entire gradient. So one thing that we can just do here would be to sum the values just to get like a single element instead of iterating over multiple times over the gradient. And we can do the same for B, because B also happens to be a vector at this point in time. Let's just sum over this. So we should be now we should be getting scalars, and W should just be basically the direction. So that's pretty much it. I mean, we have basically this is our gradient descent. It's pretty arbitrary that we're picking 10 iterations, but you know, that's reasonable. So let's try to run it all. All right, so basically what we should have now is a function that shows a little bit closer, models closer what the actual value of our truth table is for particular values. So again, we're going to do the weights, W and B. And when we evaluate these, we get these weights, right? And then we can say, let's make sure that this is higher than 0.5, which would be the activation, and compute this particular value. So as you can see here, everything is true, which is not what we want. So we probably have an error somewhere in here. Yeah, so let's just take a look at this solution that I prepared before and see if we forgot anything. Oh, actually, okay, yeah, so this is fine. Actually, the way that I wrote it is like this, but it just doesn't matter. And then we're doing the sum times the Pmax, the value, and then x1, 2, and we also have the Pmax. Yeah, this is actually pretty close to what I had. One thing that we're doing, which is again not ideal, is we're changing values, right? So if we're gonna do this optimization, we shouldn't be changing the values while we are basically executing the gradient, and that this might be the reason why we're getting different values, because it's changing within the actual computation of the gradient, which is not something that we want. So let's give it another shot to define it in this way. We still have the same issue. Let's see if we're missing anything else. The x, y. Let's see, did we define the truth table correctly? Yes, we did. Yes, we did define it correctly. We define our function. Let's see, w, x, y. Oh, yes. So this is actually silly. So I'm actually only running one iteration. If, that seems to be the problem. So if we execute this code, like actually we're just doing from I in 10, which is just happens to be 1. What we really want to do is actually run it 10 times, right? Right, so before we were actually basically just training a single iteration. We need to train them all. All right, so this should be much closer. Okay, let's rerun this, and we're getting still the same value. We're probably still missing something else to fix. Let's see. 2 times the sum. Oh, is the oh, I see. Okay, so this was my fault. Let's see. Yeah, when we're doing the learning rate, we want to multiply against the entire. Yeah, so one of the things we want to do is, you know, I was mentioning that this was an optimization that we were doing in this particular case, but we need to get it right, which would be to sum it once at a time. Otherwise, yeah, I wasn't computing the right concept here. All right, so yeah, we want to basically compute first W1, and then we want to compute W2. So let's rerun this. And of course, we have an error here. Let's see, like this. Oh, we have an extra parenthesis. All right, let's try this again. So now we're still not quite there yet. So why are we not there yet? We have WXB, X1, we initialized the weights properly. Let's see, what else are we missing? This actually looks pretty close. Oh, step. Oh, great. We missed the learning rate here, right? Yeah, and this is why, and we actually have an extra. Okay, let's see. Let's do it carefully. Right, so learning rate times 2 times, yeah, it's 2 times the we'll have a mistake here. Right, it's 2 times the actual value of the loss function, and then we're differentiating the inside, and then we're actually computing the last step. And parentheses-wise, I think this is all we need. All right, let's see. All right, this looks hopefully better. See, so that's our value, and what about our function? No, it's still, we're still missing something. Let's see. F1. Is this one working properly? Let's just try that out. Oh, well, actually, I don't know what I'm talking about. This is actually has been correct all the time. Because, oh, is it correct all the time? No, actually, no, let's see. Yeah, this is the right value. These are the right values that we want. We want something that looks like this. And the values that we actually have right now are a little bit different. Oh, no, actually, they're the same values. Let's see. Yeah, they are the same values. Yeah. Oh, right. So let's see. Oh, this is correct. What was I doing before? I don't think I was rerunning. Anyways, yeah, so this looks actually correct. So what we want to do is, I don't think I changed. Did I change anything? Yeah, I think the last iteration we have is correct. I was when we were rerunning, we were just not getting the right. Oh no, we still wrong. Let's see. We'll try to fix it. 0.2, 0.2, 0.3 of these values. Sum of a learn rate. And at this point, the function is the same actually. You have F1. Oh my god, this is ridiculous. All right, this is why, you know, training by hand can't get that easy. We were mentioning that you know, the value of our gradient descent is basically this one, right? Like we do the gradient over the previous step, and what we're missing here is we want to do b minus, right? Yeah, this is ridiculous. I mean, what we were doing before, we were just mostly incrementing b. We want to find we want to anchor in the current value of v, and then basically subtract the actual gradient with the learning rate. Do we have even the learning rate here? No, we're also missing the learning rate. Right, so this one, it's almost complete. All right, so this is looking much better. Oh no, actually this is still not looking. This is looking much better. So we have the value of v minus the learning rate times the gradient for that particular derivative, which is over b. Right, let's just rerun everything, and now we should get the correct values of the truth table, right? Okay, so this makes sense. Now we have false, 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 true, which match basically what we want, right? The output that we want this neural network to train on is basically logical of y. Oh, let me just do this. Basically, what we want is to all of them be true, right? We want to the output to equal the output of the function, right? And the cool thing about neural networks is that now we can train something else, right? Like we can use the same process. And if we wanted to train the OR function, which is basically a function that is true whenever any value from any input is true, right? We could basically retrain this same network, and we should be able to see which are the values that are bigger than this particular network, which is basically all of them except when both values are false. So again, this is pretty great. Sorry that it took a little bit more, few more iterations to solve this. But you know, again, if you try to do this by hand, you will probably hit mistakes that are quite hard to debug, because it's not just about code. You also might be messing up the differentiation, or you might be messing up the translation from the gradient into the actual code and the steps and whatnot. Anyway, so a couple of things to mention here is that right now we train using gradient descent, right? Which is the most straightforward way. There's another variation of gradient descent which is based on basically batches, right? So in this particular case, what you can also do is you can, your main loop, when you're training your batches, can split your input data and your training set into batches, right? So you basically, we usually call an epoch when we finish one iteration of training all the batches. And each batch could be a subset of your training set. So in this case, if we had like a really long matrix, right, of inputs and outputs, and if we couldn't compute all the values in a single iteration, we could basically, what stochastic gradient descent tells us is that we can split these into I in batch, and this batch could be a subset of our training set, and it would still should still converge, right? So that's one approach. The other approach, which is actually much more interesting, it's called backpropagation. And again, in the core, backpropagation is also gradient descent, but the way you do it is a little bit different, which happens to be quite useful for deep networks. So if you have if you have a really complex function, instead of differentiating it one by the entire function by itself, you can use the chain rule. And basically, what the chain rule tells you is that if you look at a network, right, when you're applying chain rule, if you look at a network like this one, what the chain rule tells you is that the only things that you need to know when you're training this particular perceptron during backpropagation are you only need to know what are the error rates that came out of this particular from the previous unit, and you also need to know what are the values of the gradient and the function. So if you can compute the gradient, if you can differentiate each function for each layer in the network, basically what you can do is, you can automate this process by saying, oh, I don't really need to do that much math. All I need to do is apply the chain rule, and when I'm performing backpropagation, I only need to basically consider what are the input values from the forward entries, and what is my internal state regarding the current, what are the weights that I need to change. So if you can isolate that particular problem with the chain rule to a single network, you can create an algorithm that basically will apply gradient descent without actually having to worry about how the math looks like. And there's a great video worth sharing, which is from Andrej Karpathy. And basically what he shows is that, you can actually create what is called a computation graph. And a computation graph is basically just a way of saying that you can represent this particular function. For instance, in this case, the function that where backpropagation is getting applied is x plus y times z. And instead of seeing this particular function as a function on its own, you can see it as a network of functions that are getting applied. For instance, you can see it as plus between x and y, and then you can have another node, which is the times. And basically what this allows you is to perform automatic differentiation. If you can define a network of operators, and then you can compute gradient descent using the chain rule, one node at a time, you can basically compute the gradient of this network, which happens to be that complex, but you can basically compute this network programmatically rather than doing it by hand. And the really nice reason why you want to do this is because this would allow you to create packages like TensorFlow that actually do the automatic differentiation for you. And obviously, you don't need to create a package like TensorFlow. You can just make use of TensorFlow. But when you define layers and when you add layers in keras or in TensorFlow, basically what you're creating is a computation graph that defines what are the inputs, what are the outputs, and how the how data is being processed in this particular mathematical function, and then TensorFlow can optimize this particular model and compute the gradients using back propagation. And then, there's other optimizations that go into TensorFlow, like, if you have a GPU, this can get executed in a GPU, and why not? But in general, I hope that this video gave you a pretty reasonable idea of how to perform gradient descent. And when you start working with keras and TensorFlow, hopefully this gives you some insight as to what is actually happening under the covers on TensorFlow when you're trying to train more complex models. Well, thanks again for listening. I hope this was a useful video, and yeah, we'll keep in touch. Thank you.